Hi, my name is Scott Simpson, and today we'll be talking about equilibrium constant expressions. So you may know what the equilibrium constant is, where you're looking at the rate of the forward reaction versus the rate of the reverse reaction. They're equivalent to one another. But now when we start considering what are the concentrations of different species at in the point where you have reached chemical equilibrium, how much products, how much reactants, what will you have actually in the situation? So before we can do that, we have to assess how to come up with this equilibrium constant expression that's throughout almost all of general chemistry, analytical chemistry, and talked about quite a bit in physical chemistry. So let's say we have generic reactions. We're going to be given the generic reaction where we have A with a coefficient of lowercase a, that's an aqueous state. We have lowercase b, uppercase B, aqueous, and it's in chemical equilibrium with two products, lowercase c, uppercase C, and then the coefficient of lowercase d, uppercase D, aqueous. So we want to derive an equilibrium constant expression for this. So the equilibrium constant expression in terms of concentrations, because there are a couple different equilibrium constants. You could have it in terms of pressure, concentration, even molality. In our case, we're going to keep it in terms of concentration. In terms of concentration. And a lot of times in your books, you'll see K sub C, where that C stands for concentration. So we're trying to write the equilibrium expression for this generic reaction. So we would have Kc is equal to, and it's always products over reactants. So we have concentration of products raised to some subscript value, or superscript value, excuse me, reactants. And these coefficients, they come just from the balanced chemical equation. So in our case, our products, our two products are C and D. So we would have C raised to the power of little c for that coefficient out front, times D raised to the power of lowercase d, divided by A raised to the A, B raised to the B. Okay, so this looks pretty simple, but there are some guidelines that you have to follow. So let's make some notes about this. You could have a situation where, since these are in concentrations, they have the symbol molarity or the unit of molarity. Something kind of strange, even though I tell my students follow the units all throughout general chemistry, when it comes to KCs, or most equilibrium constants, there is no unit associated with that equilibrium constant. And that's just set up by definition. So K sub C has no units by definition. It's just a number. That's all it is. The other important point is pure solids and pure liquids are excluded from the equilibrium constant. The reason for this is if there are two trains of thought you can go with. One of the simpler explanations is if you consider a pure solid or a pure liquid over the course of the reaction, its concentration doesn't change very much. I'll have another video about that and why you exclude pure solids and pure liquids, but that's one of the reasons. The other reason is if you've taken some physical chemistry courses or you know something about what is known as the chemical potential. The chemical potential is actually related to the equilibrium constant. And if the chemical potential doesn't change, then you exclude that substance from the equilibrium constant. So when we consider pure solids and pure liquids, the chemical potential of those systems is not changing, therefore they're not involved in the equilibrium constant. So let's summarize that. Pure solids and pure liquids are excluded from the equilibrium constant. Expression. The long answer to this is that the chemical potential of these systems is not changing. The chemical potential does not change. And their concentrations don't change very much, so we can assume this to be true. Okay, so let's look at some examples. Example, determine the Kc expression for the following reactions. So the first reaction we're going to look at, 2Ki aqueous reacts with chlorine gas. That's an equilibrium. We get KCl aqueous, that means a 2 out front, and then we get iodine gas. So the very first thing that you want to look at is you want to determine what are the physical states. In this case, we have aqueous and we have gaseous species. So that means everything is going to be included in the equilibrium constant. If we saw a liquid or a pure solid, we again exclude those from the equilibrium constant. So Kc, remember again, it's always products over reactants. So one of our products is potassium chloride, KCl. And since there's a 2 out front, we need that 2 up top here. Then we have iodine, I2. Okay, now what about the denominator? In that case, again, we have Ki because it's aqueous. There's a 2 there, and then we would have Cl gas. So that looks pretty simple. Let's move on to a more complex one. B. Let's say we have tetraphosphorus dioxide in an aqueous solution plus liquid water. Gets us phosphoric acid. We have to balance this out, so let's put a 4 here. 12, 6 there, do all of our oxygens, 4 times 4, 16. Yep, everything should be good. Okay, so now let's write out the equilibrium constant expression here. So remember again, it's always products over reactants. In this case, we have just 4 phosphoric acid, or excuse me, 4 phosphoric acids as our product. So we need H3PO4 raised to the 4th. Then we, again, have to consider those physical states. If we look at tetraphosphorus dioxide, it's an aqueous, but then we have 6 waters. Since the water is a pure liquid, we exclude this from the equilibrium constant. So the Kc expression looks like this. Now, it seems kind of tricky. Again, we just toss out that water because there's a pure liquid there. Let's get even trickier. We have 2 aluminum oxides, or aluminum solid, 3 O2 gas. Now let's consider what that equilibrium expression would look like. We have Kc, and remember we have to consider the physical states. So pure solids and pure liquids are excluded from the equilibrium constant. So again, products over reactants. We have 4 aluminum solids. Since there's a solid there, we don't have to include that in the equilibrium constant, but we do have to worry about those 3 oxygens. O2 raised to the 3. Now in terms of the reactants, again, if we look, we see a solid here. So we have actually nothing in that equilibrium constant denominator. So we put a 1 there. So it's also equivalent to just O2 raised to the 3rd. So the important point to keep track of is that when it comes to equilibrium constant expressions, if you have a pure solid or a pure liquid, it's excluded from that equilibrium constant. Knowing how to do this is very important to solve these equilibrium problems when we start discussing concentrations and so on. So with that, I'd like to end. If there are any questions, please feel free to leave a comment below or send me an email. Thank you.